In today's lesson, we'll be going through section 3.5, limits at infinity. Using a visual example of f of x equal to 3 squared over x squared plus 1, the graph of this function shows that as x approaches infinity or negative infinity, the limit is always approaching 3, but never actively touching 3. This can be denoted as the limit as x approaches positive or negative infinity of the function is equal to 3. Limits at infinity are defined as when the limit as x approaches infinity of a function is equal to a real number L. For each value presented that's greater than 0, there exists a real number that is greater than 0, such that the absolute value of the function minus the real number is less than epsilon whenever x is greater than the real number, and the opposite would be said as the limit approaches negative infinity. As it approaches a real number, the real number n would be less than 0, using the same statement here, as x is less than the real number n. Some properties of the limits at infinity can include that of if two functions exist at the same time, you can use both product and addition rules, such as f of x plus g of x will equal the limit f of x plus the limit of g of x, as well as if multiplied together, they will equal the same thing if separated. Which will be able to be used if we see functions in which infinity would result in indeterminate form. One rule that we're going to constantly be using when dealing with limits at infinity is that when the limit as x approaches infinity, where c is any real number and r is a positive rational number, then the limit will equal 0. The same applies if x of r is defined when x is greater than 0, or less than 0. I'm going to use the example from the slides in order to show off these rules and properties. So by finding the limit as x approaches infinity of 5 minus 2x squared, we could see that we have the ability to separate these into the limit of 5 minus the limit of 2x squared. And as we could see, with it being a rational number and a real number, this limit will equal 0. And as we know, the limit of 5 would equal 5. So the limit of this whole problem would be 5. And this would be infinity, so this gives us a horizontal asymptote to the right of the graph at 5. However, this only gives us the right half. We would have to double check and make sure for most problems that the limit as x approaches negative infinity would equal the same thing. Given that these rules would break down to essentially the same, the limit will still equal 5, and it will continue along the horizontal asymptote to the left, so the entire asymptote would be at 5. The other example presented to us in the slides allows us to use other methods to find the limit. We can still separate this into the limit as x approaches infinity of 2x minus 1 divided by the limit as x approaches infinity of x plus 1. However, both of these solutions present us with infinity, which is an indeterminate form. A way to circumvent this is by dividing both sides by x, which will result in us having the limit as x approaches infinity of 2 minus 1 over x divided by the limit as x approaches infinity of 1 plus 1 over x. And now we can use our rules to determine that that the limit of this will be 2 minus 0 over 1 minus 0. Simplified down to just 2. Which gives us our horizontal asymptote to the right. And as we know, taking negative infinity will present us with the horizontal asymptote to the left. We always have to check it because we never know which functions might change when going into negative or positive directions. Some guidelines when finding the limit of rational functions at infinity are all determined by the degree of the actual function. So if the degree of the function, if the numerator is less than the degree of the denominator, then the limit of the rational function will be equal to 0. If the two degrees are equal to each other, then the limit of the rational function is the ratio of the leading coefficients. So the limit of this would be 5/10. However, if the numerator has a larger degree than the denominator, then the limit does not exist. It is also possible to find that a limit of infinity can equal infinity if the value will consistently, such as this function x of 3, increase without bound, or if the same function would consistently decrease without bound. This presents an infinite limit at infinity and shows that we will always need to be checking both sections, whether it's positive or negative infinity, because the values can in fact be different. All the rules presented will be able to assist us in finding any limit at infinity. Thank you.